In today's lesson, we're going to be looking at the last discrete probability distribution that we'll be taking a look at in this course, and that's the Poisson probability distribution. Now, up until this point, all of the distributions that we've looked at have more or less followed the same formula, which is that we're going to be doing sort of repeated experiments of something where we sort of fix the number of experiments that we're going to be doing. The Poisson probability distribution is the first one that sort of follows a different format, and it's going to be very useful for capturing a lot of processes that didn't really neatly fit into the frameworks we've outlined so far. So just like when we were introducing any of the other probability distributions, the main objective for today is to understand the Poisson distribution, its use cases, its properties, and so forth. The other thing that we'll introduce today is the Poisson process. And so this is related to the probability distribution, and it's a very useful way of capturing real-world phenomena. So you want to understand what that is as well. So the example that we're going to use for the Poisson probability distribution is actually car accidents, right? And if you're, say, working at an insurance company and you want to know how likely is it for there to be a car accident, you could try to fit this into say, a binomial distribution, right? Where we're sort of running repeated experiments with the different cars and seeing if any of them get into an accident. But that's not going to really be the best way of thinking about that. And the reason is that with car accidents or other types of accidents, what we're really thinking about more is that we're observing for some length of time, and there's sort of any number of accidents that could occur within there, right? We're just sort of watching until they happen. We're not doing repeated experiments. We're sort of just observing, and then the events occur or they don't occur, sort of at any instant in time, right? And so when we have this sort of different mindset where it's an observation window is the experiment, then the types of distributions that we've looked at so far that are dependent on this repeated observation or repeated experiment framework don't fit as nicely. And so that's where we're going with the Poisson probability distribution. So as I was just mentioning, because oftentimes in the real world we don't really have these repeated trials frameworks, we need other types of distributions. And so anytime that we're counting the number of occurrences of an event over a fixed window of time, or perhaps in a sort of fixed window of space, right? So if you want to know you're producing rope and you want to know the amount of defects in a certain length of the rope, or you're looking at sort of the distribution of particles out into a solution. All of these things where you're sort of counting the occurrences of something over a window of time or space, that's going to follow a Poisson distribution. Now we can write down the PMF of a Poisson distribution. It's going to be characterized by what we call the rate parameter, and we write that as mu, right? And the PMF is going to be given by e to the power of negative mu times by mu to the power of x divided by x factorial. And this is going to be defined for x equals 0, 1, 2, and so on, any positive or non-negative integer. We can write down that the expected value of x is going to be mu, and also that the variance of x is going to be mu. So the Poisson distribution has this really interesting property where the mean and the variance are always going to exactly equal one another. Now, typically what we're going to think about is counting the number of occurrences of events during a period of time. And while the Poisson distribution can be used directly, it's often more convenient to use what we would call the Poisson process. Okay. And so in order to use the Poisson process, what we're going to be thinking about is that events are happening at a constant rate of alpha per interval of time. So events occur at a rate of 1 per hour or 10 per week or whatever else, right? So there's going to be some rate per unit of time. And we want to know about the number that are going to occur in some interval of time, which we'll call t. Now, we're going to assume that all of the events are independent of one another and that no two events can occur at exactly the same moment in time. Okay, so there has to at least be separation of them in some sort of minimum interval. if we're making all of these assumptions, what we find is that this is going to be well described by a Poisson alpha times t distribution. So a Poisson distribution where the rate is alpha times by t. So if I tell you that something happens 10 times per hour, and we want to think about over the course of 5 hours, how often is that going to happen? Well then, 10 times per hour times by 5 hours, this is going to follow a Poisson with a rate of 50. Okay, so it's sort of the natural way to generalize these things, but what this allows us to do is specify a rate, specify a time period that we care about, and then sort of get the distribution out of that based on these assumptions for free. Now, we are implicitly assuming that there's some sort of concordance between the rate and the time interval. So if I tell you that the rate was 5 per minute, and then I say the time interval is 1 week, well, you're going to have to convert the 1 week into minutes. But beyond that, you can just take alpha times by t. Now, we can also think about relating the Poisson distribution to the binomial distribution. And this is linked in the limiting behavior. And so intuitively, if you think about taking more and more binomial trials, where each of them is sort of very low probability of success, then this is similar to waiting for an event to occur, right? So if you think about whether or not an accident happens, one way you could do that is just observe some stretch of highway continuously, right? But another way that you could do it is say, every few seconds having an automated picture be taken and see if at any point there's going to be a accident being taken there. And so there you're thinking of taking more and more successive pictures in smaller and smaller windows of time. So mathematically, if we take n towards infinity and we take p towards 0, such that the product of the two of them is going to equal mu, right? So you're doing this at in such a rate so as to fix the rate at which n times p occurs, then we can approximate the binomial distribution with a Poisson distribution. And so the general rule of thumb that people give is if n is bigger than 50 and both n times p and n times 1 minus p are less than 5, then you can use this sort of distribution here. Now, with all rules of thumb in statistics, this is just going to be general guidance. And the need for this type of approximation is actually minimized nowadays because we can just use software to compute all of these probabilities. But there are still going to be times where working with the Poisson distribution is slightly easier than with the binomial distribution. And so in those cases, it's good to know that they share a limiting distribution. So once again, just a brief introduction to the Poisson distribution. Note that the Poisson distribution is a little bit different than the distributions we've seen up until now. It's going to count the number of occurrences of events in an interval of time. We saw that it has a PMF, expectation, and variance. The Poisson process is a way of capturing the arrivals of events based on a certain rate and time interval. And we can view the Poisson distribution as the limit to the binomial distribution as we increase the number of trials. So with that, we're sort of wrapping up talking about discrete random variables, and then we'll introduce the concept of continuous random variables in the next lesson. So I hope to see you all there.